This is SpaceTime Series 27, Episode 144, for broadcast on the 29th of November 2024. Coming up on SpaceTime, a new discovery challenges our current understanding of how planets are formed. A new theory reveals the shape of a photon. And NASA's Swift Space Telescope celebrates 20 years of discovery. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered an exoplanet that's just 3 million years old, and that challenges our current understanding of how quickly planets can form. The newly identified planet, Taade 1b, orbits its host star once every 7 Earth days. It's providing scientists with a glimpse into the early stages of planetary formation, setting a new benchmark for young planets and marking a step forward in our understanding of planetary systems beyond our own. The study's lead author, Madison Barber from the University of North Carolina at Chapel Hill, says current evidence suggests that it took the Earth between 10 and 20 million years to form. So Taade 1b's 3 million year age comes as quite a surprise. Discovering planets like this one allows scientists to look back in time, catching a glimpse of planetary formation as it's happening. Taade 1b is the youngest known transiting planet, and as such offers a unique window into the environment of an emerging planetary system. This discovery sheds fresh light on the potential differences between our solar system and other star systems hosting close-in giant planets like Taade 1b, providing a greater context for our own cosmic neighbourhood. This discovery also opens new research avenues as the planet is still within its natal disk of material, allowing scientists to study the formation process up close. Follow-up studies will analyse how the planet's atmosphere compares to the surrounding disk material, providing clues about its journey into its compacted orbit. Barber and colleagues will also examine whether Taade 1b is still growing by accreting more and more material, or possibly losing its upper atmosphere due to the influence of its host star. Planets typically form from a flat protoplanetary disk of dust and gas, which is why planets in our solar system are aligned mostly in a pancake flat arrangement. But in the Taade system, the disk is tilted, misaligned with both the planet and its star, a surprising twist which challenges our understanding of how planets are formed. A report in the journal Nature says the technique used to detect this planet makes its discovery especially significant. Now, typically, planets on the edge of their solar system this young are impossible to observe due to the interference of the surrounding disk. However, because this star's disk is warped, it allows a rare observational opportunity. The authors employed a specially designed search algorithm called Notch and refined data extraction methods from NASA's TESS mission in order to detect and confirm the planet's existence. And now the real work of studying this oddity, if that's what it is, can begin. This is SpaceTime. Still to come, a new theory reveals the shape of a photon, and NASA's Swift Space Telescope celebrating 20 years of discovery. All that and more still to come on SpaceTime. A new theory that explains how light and matter interact at the quantum level has enabled scientists to, for the first time, define the precise shape of a single photon. Photons are individual particles of energy or light. The new findings, reported in the journal Physical Review Letters, explores the nature of the photon in unprecedented detail, showing how they're emitted by atoms or molecules and are then shaped by their environments. The nature of this interaction leads to infinite possibilities for light to exist and propagate or travel through its surrounding environment. These limitless possibilities, however, make the interactions exceptionally hard to model, resulting in a challenge that quantum physicists have been trying to address for several decades. By grouping these possibilities into distinct sets, scientists with the University of Birmingham were able to produce a model that describes not only the interactions between the photon and the emitter, but also how the energy from that interaction travels into the distant far field. At the same time, they were able to use their calculations to produce a sort of visualization of the photon itself. And yes, it looks like just a sphere with different levels of light. Photons are fundamental quantum mechanical elemental objects that are both waves and particles. You see, neither description by itself fully captures all of their characteristics. And it's this particle-wave duality that makes photons difficult to pin down. The study's lead author, Benjamin Nguyen, says the new calculations enable this team to convert a seemingly insolvable problem into something that could be computed. And almost as a byproduct of the model, they were able to produce an image of the photon, something that hasn't been seen before in physics. Now, this work's important because it opens up new avenues of research for quantum physicists and material science. By being able to precisely define how a photon interacts with matter and with other elements in its environment, scientists can design new nanophotonic technologies that could change the way we communicate securely, detect pathogens, or control chemical reactions at a molecular level. It turns out the geometry and optical properties of the environment does have a profound consequence for how photons are emitted, including defining the photon's shape, its color, and even how likely it is to exist. Ewan says the work helps to increase science's understanding of the energy exchange between light and matter, and to better understand how light radiates into its nearby and distant surroundings. Now, a lot of this information had previously been thought of as just noise. But there's so much information within it that physicists can now make sense of it all, or at least some of it. And they can make use of that. By understanding this, they set the foundations to be able to engineer light-matter interactions for future applications, such as better sensors, improved photovoltaic energy cells, and quantum computing. In the process, opening up a much brighter world. This is SpaceTime. Still to come, NASA's Swift Space Telescope celebrates 20 years of discovery, and later in the science report, researchers unravel the DNA history of modern-day cattle. All that and more still to come on SpaceTime. NASA's gamma-ray burst-hunting Swift Space Telescope has just celebrated its 20th year in space. Over the past 2 decades, the Earth-orbiting observatory has made great scientific strides, helping astronomers identify what up until then had been one of the greatest mysteries in science, the source of gamma-ray bursts. Gamma-ray bursts were first detected back in the 1960s by American spy satellites monitoring the Soviet Union's compliance with nuclear test ban treaties during the height of the Cold War. See, atomic bombs give off powerful bursts of gamma radiation during their detonation, and the United States have a network of satellites which can detect this. Trouble is, they were detecting hundreds of these blasts every year, not in the atmosphere or on the ground, but out in deep space, well beyond the moon. Now, not only did this mean the Soviets were cheating on the treaty, that wasn't surprising as the Communists already had a long history of breaking agreements, but it also meant they must have hundreds, possibly even thousands of spare nuclear weapons for these tests, and certainly far more than the West. It also meant they had hundreds of spare rockets to launch all these bombs into deep space for testing. And they could do it both far more reliably than the Americans, and without the West even detecting the launches. Now, if all this was true, it meant the Russians' technology was far in advance of anything the free world had. In fact, the West may never be able to catch up. If that's the case, the Cold War was already over and the Communists had won. Because of the implications, the whole thing was declared top secret, while the military considered its next course of action. Luckily, eventually, the Pentagon allowed astronomers to have a look at the data. And astronomers quickly determined that all these events were taking place billions of light years away, far beyond any human technology, and certainly well beyond the capabilities of the Soviets. So the crisis was over. But the cause of these extraordinary gamma-ray bursts would remain a mystery for decades to come. Gamma-ray bursts, you see, are the most powerful explosions in the universe since the Big Bang. But they're highly ephemeral, only lasting a couple of seconds at most. A gamma-ray burst will appear somewhere in the sky without warning, roughly once every day. The typical gamma-ray burst releases as much energy in a few seconds as what our sun will produce during its entire lifespan. But there was one clue. See, while the actual burst itself usually lasts a few seconds, it generates a faint afterglow which can be observed for several minutes, sometimes a few months, and occasionally even a few years. Trouble is, in the beginning, it was difficult for astronomers to study gamma-ray bursts because of the time taken to notify observatories around the other side of the world to stop the important work they were doing so they could point their telescope towards the location of the gamma-ray burst. And that's where NASA's Swift Space Telescope comes in. It was developed to give astronomers a quick response observatory, almost instantly being able to point at the location of a gamma-ray burst. And it's thanks to Swift we now know the origins of gamma-ray bursts. They can be categorized as either short period or long period, depending on their duration. About 30% of gamma-ray bursts are catalogued as short period bursts. These usually last less than 2 seconds, with 200 milliseconds being the average. They're thought to originate from either binary neutron star mergers or mergers between neutron stars and stellar mass black holes, resulting in what are commonly called kilonova explosions. On the other hand, those over 2 seconds, which make up about 70% of all gamma-ray bursts, are categorized as long-period bursts, and they're associated with galaxies featuring rapid star formation. They've been linked to the core collapse of massive stars in supernova events, creating stellar mass black holes. Swift uses several different methods for orienting and stabilizing itself in space in order to find and study gamma-ray bursts. Sensors that detect the sun's location and the direction of the Earth's magnetic field provide the spacecraft with a general sense of its location. Then there's a device called Star Tracker. It looks at stars and constellations and tells the spacecraft how to maneuver to keep the observatory precisely pointed in the same position during long observations. Swift uses 3 spinning gyroscopes to carry out these moves along its 3 axes. The gyros were designed to align at right angles with each other, but once in orbit, scientists discovered that they had been slightly misaligned. The flight operations team eventually developed a strategy whereby one of the gyros worked to correct the misalignment while the other 2 pointed Swift to achieve the science goals. However, the team also wanted to be ready in case one of the gyros failed, so in 2009 they developed a plan to operate Swift using just 2 gyros. But of course, any change to the way a telescope operates once it's in space carries risk. So, since Swift was working well, the team sat on their plan for 15 years. That was until July 2023, when one of Swift's gyros began to fail. Because the spacecraft couldn't hold its pointing position accurately anymore, observations progressively got blurrier, until the gyro fell completely in March this year. Because they already had the shift to 2 gyros planned out, scientists were able to quickly and thoroughly test their procedure on the ground before implementing it on the spacecraft. And it worked. For the last 20 years, Swift has contributed to groundbreaking results, not only for gamma-ray bursts, but also for black holes, stars, comets, and other celestial objects. Swift's principal investigator, S. Bradley Senko from NASA's Goddard Space Flight Center in Greenbelt, Maryland, says that after all this time, Swift remains a crucial part of NASA's fleet. In fact, the satellite's abilities have helped pioneer a new era of astrophysics known as multi-messenger astronomy, and that's giving scientists a more well-rounded view of how the universe works. This report from NASA TV.
Satellite names aren't always easy to understand, but NASA's Neil Gehrels Swift Observatory states its key ability up front. Launched on November 20th, 2004, Swift is first and foremost a rapid-response gamma-ray burst explorer. Gamma-ray bursts, or GRBs, are the most powerful explosions in the universe. They arise when massive stars run out of fuel and collapse, or when pairs of orbiting neutron stars collide. GRBs can be as brief as a few milliseconds and happen in distant galaxies, which makes them hard to spot. Despite this, Swift has managed to observe 1,800 GRBs. Scientists and engineers designed Swift's GRB detector to see large portions of the sky and quickly relay a GRB's location to the ground, so other missions could follow up. They also enabled Swift to change where it's looking very rapidly, so it can target its X-ray and ultraviolet optical telescopes on any detected event. Swift owes much of its existence to Neil Gehrels, who was a scientist at NASA's Goddard Space Flight Center. Neil was a global figure in gamma-ray astronomy, and gamma-ray bursts in particular. He was part of the small group that first imagined Swift in 1998, and was instrumental in seeing it through to launch and into its early mission. After Neil passed away in 2017, Swift was renamed in his honor. Over its 20 years of operation, Swift has proven incredibly useful and versatile. Its rapid detection, alerts, and repointing have allowed missions like NASA's Chandra, Webb, and Hubble to quickly follow up on transient events. Beyond GRB detections, Swift's X-ray and ultraviolet optical telescopes have enabled it to perform science that no one imagined prior to launch. Swift has tracked near-Earth asteroids, observed more distant asteroid collisions, studied comets, seen massive flares on distant stars, taken ultraviolet surveys of nearby galaxies, and made countless observations of short-lived cosmic phenomena. Despite the failure of one of the spinning reaction wheels that enable Swift's rapid turning, the spacecraft remains as nimble as it was in its first year, and it promises to remain a critical first responder in NASA's astrophysics fleet.
And time now to take another brief look at some of the other stories making news in science this week with the Science Report. New research warns that people on blood-thinning drugs double their risk of an internal bleed if they start taking a type of painkiller known as a non-steroidal anti-inflammatory, such as ibuprofen. The findings, reported in the European Heart Journal, looked at data from 51,794 Danish people who had been taking blood thinners for blood clots, finding the risk of a bleed was 2.09 times higher among people taking non-steroidal anti-inflammatories compared to those just taking the blood thinners. The risk for ibuprofen was 1.79 times higher. For the non-steroidal anti-inflammatory diclofenac, the risk was 3.3 times higher. And for the non-steroidal anti-inflammatory naproxen, the risk was 4.1 times higher. The authors looked at several types of blood thinners and found a similar risk pattern in all. A new study has looked at the DNA history of an extinct group of ancestors of modern-day cattle, showing a complex ancestry. Modern-day domestic cows are all descended from aurochs, a large species of wild roaming cattle that lived up to 650,000 years ago but have now been extinct for at least 400 years. A report in the journal Nature looked at 38 ancient auroch genomes, finding 4 major ancestry populations across Europe, Southwest Asia, Northern Asia, and South Asia, spanning some 47,000 years. It seems each of these ancestries responded differently to climatic changes and human pressures, with the Southwest Asian aurochs contributing the most genetically to today's domestic cattle breeds. A new study has shown scientists that the boundaries between solid and liquid metals can be far less solid than previously thought. A report in the journal Advanced Science claims researchers have discovered that the liquid-solid boundary can fluctuate back and forth, with metal atoms near the surface breaking free from their crystal lattice. Observing a metal alloy mass solidifying in a sea of liquid metal, the team saw a phenomenon never seen before. The surface metal moves from a solid state into a liquid state and then back again at unexpectedly low temperatures, far below the melting point of the solid metal. The new discovery has potential applications wherever metal alloys are being utilised. Psychologists say the human brain is pre-wired to believe in the supernatural. A new book looking at the science behind some of the weird stuff we interpret points to 6 simple ways in which your mind is pre-programmed to conjure up the supernatural. Tim Mendham from Australian Skeptics says it's just the way the human brain works.
This is a story written by 2 noted skeptics, Chris French, who runs the Centre for Anomalous Psychiatry or Psychology in London, at London University, and Richard Wiseman, who's another psychologist and a well-known skeptic. And they talk about various reasons why people might believe in ghosts especially, and also just general supernatural things, premonitions, reincarnation. They expect, first of all, for instance, that one of the key factors in why people believe is an expectation, what they call an expectation effect, which is basically to say they want to see it and what they expect to see, and therefore they see it. This is sometimes called a top-down processing effect. top-down process is the same effect as behind most optical illusions. You expect to see something and you see it, and that explains also faces, the man in the moon,
that would have been important back in the day when we were chasing dinner around the bush and hoping not to be eaten by a lion.
Well, that's exactly right. And this is something you spot some. You expect, you have to be aware, but then that comes to the second suggestion that they make, which is pattern spotting, that they hear or see something that fits a pattern, and that therefore means that if they hear a lion or hear what they think is a lion, it's advisable to run away, and the person who stops and waits to find out might not be
might not be around to verify.
Yeah, might say, whoops, I made a mistake. Expectation, effect, and pattern spotting are very similar. I want to see something, so I do see it, and that's why a misleading statement by, say, a psychic or something can be latched onto as something real because the person wants to believe. Most people who go to psychics do it because they actually believe in psychics, even if they take it as a bit of fun, etc. They do have a propensity to believe, so they're halfway there already, and that's what every con man or otherwise, or every psychic or that sort of thing relies upon, the person's willingness to believe. Then there's all sorts of things that people see, which is, as we discussed before, about facial recognition. You see faces everywhere.
Pareidolia.
You see pareidolia. You see it in everything from taps to science to clouds to you name it. Faces especially, but other shapes as well. So you can see things which actually aren't there, but because it's so familiar in the shape, you want it to be there. Unconscious powers, what's something that's called the ideomotor effect, which is when your hand moves unknowingly, unconsciously, little tiny movements.
Oh, this is Ouija boards and things like that.
Talk about Ouija boards and put your fingers on a Ouija board and start spelling out letters and things like that. They suggest that if you're going to do a Ouija board session, put blindfold on everybody and then see. We have one person without a blindfold who can take notes. But then see if you're actually spelling something. There's an unconscious movement in your hand. You're not cheating as such, you're just pushing. The same way for water divining, dowsing, when the rods move, etc. That's often been explained with the ideomotor effect. You want to find water, you will find water, or you'll find a reaction to what you think is water, and that's a big difference as well.
And if you dig down deep enough, you'll find water anyway. There's a water table.
You should, yeah. You should in most cases, and surprisingly, actually, how often they don't find it, which indicates that perhaps they're
well,
not
they don't remember those ones, do they? Those ones
no, of course not. No,
doesn't reinforce the positive they want to reinforce.
Then there's false memories. You think you saw something, or perhaps you didn't see something, but someone tells you saw it, and then you will believe you saw it.
Yeah, if you're told something enough, you tend to believe it, even if it didn't really happen.
That's right. That's right. And this has been shown to be very, very true, that the memory is not a video camera or a tape recorder. It is a very malleable thing. So we have articles, we've got an article about this in the next issue of our magazine, is that you can manipulate it either unconsciously yourself or by desire, or someone can manipulate you. And this is often used in sort of magic tricks and things. Look, this spoon is bending by itself, sitting there, and it's sort of, people say, oh, yeah, I can see it, but they never did. And that links up with predetermined conclusions and brings you back to the start. I want something to happen. I think something's going to happen, and therefore my eyewitness accounts, my memories show me that it did happen. And all those things are fooling yourself, really, and not, necessarily in a nasty way, but it is fooling yourself into believing ghosts, premonitions, psychic powers, a lot of paranormalities, and it's a fascinating thing. It's very, very human, very normal, nothing particularly evil about it, but it's just other explanations and saying it's a ghost.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.